Okay, so before we get started, I told you guys that it would be a very good idea if you keep going to the website and to the forum. So I hope you all went to the forum. There's a small mistake in one of the questions of the homework, and so I'll post a correction there today. This is problem number 4. Is that right? Yeah. So I'll post a corrected version of problem number 4. It's almost correct. There's a little technicality that's wrong, but I'll fix that. Okay. So let's see. We are talking about Groebner bases, and last time we finished by proving a theorem that if you fix a monomial order, then any ideal has a Groebner basis with respect to that order. So that was the question of existence. And today I want to talk about two questions, which are how do you recognize a Groebner basis and how do you construct a Groebner basis. Okay? So that's our plan for today. So the first question is, if I give you a bunch of polynomials in an ideal, how can you tell whether that's a Groebner basis or not? And the second question is, if I just give you the ideal, then how do you come up with a list, a Groebner basis? Okay. And I want to make this discussion very concrete, so I would like to, let's say, I would like to do everything explicitly in an example. So let's say that this example is the lexicographic ordering with x greater than y. And the ideal that we're going to work with is generated by the polynomials x squared plus xy to the 5th plus y to the 4th. So this is 2 variables, by the way. Only 2 variables. Then xy to the 6th minus x cubed plus y 5th minus y squared, and xy to the 5th minus xy squared. Okay. And so an example of the first question is, here I have an ideal given by these 3 polynomials, which we'll call them h1, h2, and h3. And so the question will be, are these 3 polynomials a Groebner basis for the ideal, or are they not? Okay. So remember, what does it mean to be a Groebner basis? It means that if you take the initial terms of these polynomials, those guys generate the initial ideal. And so let's pay special attention to those initial terms, which in this case are the lexicographically first terms, which are these guys right here. Okay. And so the question is whether x squared, xy to the 6th, and xy to the 5th generate the initial ideal. How do I know? Well, basically what I would have to do is I would have to see if there's other combinations of these polynomials which live in the ideal and have different initial terms that are not generated by these guys. Yeah?
Shouldn't xy to the 3rd be before xy to the 3rd?
No, so and this is the lexicographic order where you don't really care about the degree. And remember that the way that I define lexicographic order, I said that you go from left to right. So you compare the x coordinate, and they have the same exponent. And you go to the second coordinate, and in this case, there's 6 y's and 3 y's here. And the guy that has more y's is going to be earlier lexicographically. Which you're right, is not exactly dictionary order. But if you look at the exact definition that I gave of lexicographic, it's what I'm telling you. You look at the first coordinate, then the second coordinate, etc. Okay? Okay. So Right, so the question is, can I find combinations of these guys that have different initial terms? And how can you try to build different initial terms? Okay. For example, let's try to use h1 and h2 to build a polynomial that has an initial term different from this one and this one. So what we might try to do to generate smaller initial terms is to try to cancel this x squared with this xy to the sixth. So let's make a linear combination of these two guys that does that. So I want to write a combination something times h1 plus something times h2, which will cancel that x squared and that xy to the sixth. So what things do I have to put here? Well, if I want to cancel this term and this term in linear combination, then what I might try to do is multiply h1 by y to the sixth and multiply h2 by minus x. Right? And that'll accomplish that cancellation. I'll get x squared y to the sixth plus, please double check what I'm doing because it's hard to do these things live on a blackboard, on a whiteboard. Minus x squared y to the sixth minus plus x squared y cubed minus xy to the fifth plus xy squared. Okay? And the point is that I cancel this guy, and then I get a new initial term. In this case, it's going to be, which one? X squared y cubed. Right? And then I have to ask, is this guy generated by the other guys or not? Right? Well, it turns out that this is okay, right? Because x squared y cubed is generated by x squared. And so at least in this way, I didn't give you evidence that this is not a Groebner basis. Okay? So this polynomial has a name. Okay? This polynomial is called S of, Lisa has a notation. We're going to call it S of h1 and h2. And it's basically the smallest combination of h1 and h2 that cancels the leading coefficient. So let me define that in general. S of f comma g is going to be a combination of f and g. And what combination is it? Well, basically, what I want to do is make these guys have the same leading term. And the way that I do that is that I multiply by the least common multiple of those leading terms and divide by the initial term of this guy. And I do that here too. Where m is the monic least common multiple of the initial term of f and the initial term of g. The point being that, I mean, what's m in that case? Well, in this case, my leading terms are x squared and xy to the sixth. So their least common multiple is x squared y to the sixth, and that's the guy that I'm going to try to cancel. I'm not going to try. I'm going to succeed, right? I am going to cancel it. And the same thing here. Monic means that it has coefficient 1.
Oh.
So in this case, the initial term of this guy is initial term of f divided by initial term of f multiplied by m. And this guy is initial term of g divided by initial term of g multiplied by m. So that means that the leading term of this guy is m, the leading term of this guy is m, and those guys get canceled. Okay? So this is somehow the smallest combination of f and g canceling the leading terms. Okay. And so maybe the first thing that I would do to check whether this is a Groebner basis is check whether these guys are generated or not. Now, you realize that in order to check whether this guy is a Groebner basis, I actually have to do this for every combination of H1, H2, and H3, right? For every combination, A1, H1 plus A2, H2 plus A3, H3, I would have to check that leading term and see if it's generated by these leading terms. But there's this beautiful theorem that says that actually I don't need to do that. I only need to do it for these polynomials. It's enough to do it for S of H1, H2, S of H2, H3, S of H1, H3. It's pretty amazing. It makes this job very easy. So this is called Buchberger's criterion. Let's say that I is generated by G, which consists of the polynomials G1 up to Gm. Okay. Then you want to know whether G is a Groebner basis. And what this criterion tells you is that all you have to do is just check these pairwise polynomials S of Gi, Gj. So for each I and j, the polynomial S of Gi, Gj doesn't give you any new things. And what this means is that if you take this polynomial and you do this long division by G1, G2 up to Gm, you get 0. So leaves remainder 0 upon long division by these guys. Okay. Now there's a little technicality here that I told you that long division might depend on the order that we divide in, right? It doesn't depend if we have a Groebner basis, but precisely that's what we're trying to determine here. We don't know if these guys are a Groebner basis. But it tells you that you can just do long division just in kind of left to right order. You divide by G1, then G2, then G3, etc., and that'll be enough. By G1, then G2, then etc., then Gm. So that's Buchberger's criterion. I should tell you that the people have a shorthand notation for this, which maybe explains it a little bit better. We'll just write this, that S of Gi, Gj is congruent to 0 mod G. So the definition of this is this one, and G is implicitly given in order G1, G2 up to Gm. So this is all you have to check. And so that's what we would have to do in this example. Okay? We would have to say, first we check S of H1, H2, and we get this polynomial. Xy to the 11 plus y to the 10 plus x squared y cubed minus xy to the 5th plus xy squared. Okay? Then we would have to take this polynomial and do long division by these guys. Takes a little while, but we know how to do it. Okay? And when we do it, we find that this thing is congruent to 0 mod H1, H2, and H3. So H1 and H2 don't give us anything new. Then you have to do it for H1 and H3. And so that means you make this computation again, but now with h1 and h3. And when you go ahead and do that, again, it takes you a little bit of time, but you can do it. And you're going to see that that's also 0 when you do long division of that guy by h1, h2, and h3. And then finally, you check S of h2 and h3. When you perform that long division, and when you do that, you are going to get this. And that means you have news. Probably bad news, because probably you were hoping that this was a Groebner basis. It turns out this is not a Groebner basis because you didn't get a 0 here. Okay? But now at least you know. So Buchberger's criterion tells you how to figure out if you have a Groebner basis or not. Okay? Any questions about how you carry this out? Okay. I'm actually going to omit the proof of this. You can read it either in Dummett and Foote, or you could read it in Eisenbud's book, or several places. And if this kind of thing interests you, then you might actually think about doing your project and the computational aspects of these things. There's a lot of nice things to say about this. But I just wanted to show you how this is actually done. Okay? Buchberger's criterion. Okay. So that's the answer to the first question. How do you recognize a Groebner basis? Well, you just perform this computation, and actually that's pretty fast to do. If you have a computer, this will take you very little time to do it. So that takes care of the first question. Now, if the answer to the first question is yes, then you're in good shape. But if the answer to the first question is no, then that leaves you unhappy because you wanted a Groebner basis, because you know that Groebner bases are useful, and you want one, right? And you don't have one yet. So, like in that example, how do we actually make a Groebner basis? Well, at least you might know where to start, right? You might know where to start because you have just produced a polynomial. And this polynomial is in your ideal. Why is this guy in the ideal? Because this thing is a combination of h2 and h3, right? And h2 and h3 are in the ideal, so that means that this guy is in the ideal. And what did you do in this congruence? What you did is that you long divided by things in the ideal. So what you did is you took something in the ideal, you subtracted things from the ideal, and so the result is in the ideal. And what you obtained here is a very explicit certificate that this is not a Groebner basis. Why? Because its leading term is y to the fifth, and that leading term is not generated by any of these guys. Okay? And so I think the natural thing to do then is say, okay, well, this is a polynomial. It's in my ideal. It's not generated yet, so let me just throw it in there and try and see if that's a Groebner basis. Okay? And that basically is Buchberger's algorithm. Okay? And that's how you answer the question number 2. So this is the answer to the first question. But the answer to the first question easily becomes an answer to the second question. Okay? So this is Buchberger's algorithm. So the input of this algorithm is an ideal and a term order. Well, let's say that you have a term order, and then let's say that your ideal is given to you. And generally, ideals are given to you in terms of generators. Okay? And what you're supposed to output is a Groebner basis. A Groebner basis for I with respect to Actually, if you will forgive me for a second, let me go back. And I want to ask who speaks Spanish here. Laura, I guess you have to do this. Whenever I write something that you would not recognize if you didn't speak English, then tell me. For example, least common multiple, mínimo común múltiplo, for everybody in Colombia. And also, whenever I write something that you don't know the meaning of, then you should ask me, and you did ask me, and I didn't. I answered you in words, but I should write it down. Monic, a polynomial is monic if its leading coefficient is 1. Leading coefficient is 1. Okay. I think that's all for now. Let's see. So, and this is something that I always assume people know what I mean, and they not necessarily know that. So when I write this, I mean with respect to. That's what makes me think of this. WRT means with respect to. Okay. So what's the plan? Well, we're going to do the following. We're going to say, the first thing is you're going to see, we're going to define G to be F, okay? And G is eventually going to be our Groebner basis, but we don't know yet if it is, okay? So eventually, this will become our Groebner basis. And we're going to define a set B, which is going to be, I'll write the notation F choose 2, and what I mean by this is the set of pairs in F. Pairs ij such that I and j are in F. Okay? And what this is going to mean is you should think of this set B as the pairs that we haven't checked yet in using Buchberger's criterion. So this is the unchecked pairs. Okay. So let's think about it here. So F here is these three polynomials, and I start by not having checked any pairs, and then I'm going to proceed pair by pair. I'm going to check H1 and H2, which is one of these pairs, and see if that's okay. So here's how it goes. While, I'm going to do this in pseudocode. While B is non-empty, that means that I'm not finished. While there are pairs that I haven't checked, then I have to basically pick a pair and check it. In this case, I might choose H1 and H2 and check it. The way I check it is that I compute this residue, right? R is S of F comma G mod G. That's this guy that I compute. If it's 0, I'm okay. If it's not 0, then I have something to do. Right? So if R is equal to 0, well, if R is not equal to 0, that means I'm going to throw in that new polynomial R into my basis, into my eventual Groebner basis. Right? I'm going to say, let G I hope you guys have done a little bit of computer science, or you might get nervous by the notation I'm going to use here. G equals G union R. That means that to your old set G, you add R. Okay? Like in this case, I'm going to add this guy H4. I mean, here, this went right, but this went wrong, and so I add H4 to my set. So I have to add it, but that means that I have to check those new pairs that are formed also, right? As soon as I add H4, well, now this guy is going to be 0 mod H1, H2, H3, H4, but now I have to check the pairs H1, H4, H2, H4, and H3, H4. So take B And I add to that all the pairs involving R. Okay. So you add the no polynomial and you add the new pairs. Okay. And then once you've done that, that means that you have already checked this pair FG, and so you just delete it from B. And you keep doing this until B is empty. So let's do this in practice now. This is the algorithm. That's it, basically. This is how you make a Groebner basis, and so we're going to do it here. Okay? So we start with H1, H2, and H3, and we start computing pairs. S of H1, comma H2 is okay. S of H1, comma H3 is okay. S of H2, comma H3 is not okay. So we take this remainder, and we call it H4. And then we start checking the pairs with H4. So we check this guy. We need to check that it's 0, except that now you're allowed to divide by H1, H2, H3, and H4 because you have a new generator. Okay? And when you take S of H1, H4, you reduce it mod this guy, you see that you get 0. Okay? Then you do it for H2, H4, and you also get 0. And you do it for H3, H4, and you also get 0. When you get to this point, then Buchberger's criterion tells you that you have a Groebner basis. Okay. So that means that these guys, I'm going to write them here. This, and this are a Groebner basis. Okay. And now we have it. And that means we can now start doing all the computational tasks that we do with Groebner basis. Okay. I think this algorithm requires no proof. The proof comes in Buchberger's criterion, but the algorithm just says do this until it works. That's not entirely true because you have to argue that this ends. Right? In theory, it could be that this goes on indefinitely, but actually that's pretty easy to check. But again, I'm going to kind of sweep that under the rug because my point is just to show you how these things are done, and if it interests you, then I'm happy to help you look into this a little bit more. Okay? But so that's how you find a Groebner basis. That's it. You see, it's actually fairly straightforward to do it. That means we have our answer to the second question. Okay? Now you know the way mathematicians are, right? Whenever the answer is too easy, then we want a harder question. So we think this is too easy, and now we want to do better than this. We think we can do better than this because this didn't take us a lot of work. And so maybe I will add a third question to this list, which is how do you construct a good Groebner basis? Well, of course, we have to decide what good means, right? But so I'll tell you what I mean by good. I mean, for example, can someone look at that Groebner basis and tell me what's bad about it? Or can you think of a better one? It's redundant. Why?
The third one is just a multiple of the fourth one.
So Andrew's telling me that I shouldn't put this polynomial in here because I don't need it. Now you see that's slightly subtle, because it's true that this guy is a multiple of this one. Okay? Which means that in the original ideal, this guy is superfluous. But we have to check that as a Groebner basis element, it's also superfluous. Okay? And that's something about initial terms. Okay? We know that to be a Groebner basis, you need all the initial terms to generate. And actually, the reason why this guy is redundant is not exactly because this polynomial is a multiple of this polynomial, but because the initial term of this guy is a multiple of the initial term of this guy. I could have an x cubed here, and this would still be redundant. Why? Because remember that we proved something, that a bunch of polynomials are a Groebner basis if and only if their initial terms generate the initial ideal. So you only care about initial terms. Okay? And if you have y to the fifth, you don't need xy to the fifth. And that means that you're not going to need this guy either. Okay? But maybe you do need this one. And so that's a very simple way to make a better Groebner basis, is just delete the junk. It's a good procedure in life for your peace of mind. So we're going to delete the junk and keep the things that don't matter. And we're going to call this a minimal Groebner basis. I think you'd agree that this is a better one than this one, because it's going to make our computations shorter. Okay. So what do I mean exactly by a minimal Groebner basis? I mean this, and I mean one more thing. So a Groebner basis G, let's say that it's G1 up to Gn, is minimal if two things happen. So the second thing is what we just said. Basically, you shouldn't have an initial term of one be an initial term of another. So no initial term of Gj should be a multiple of the initial term of Gi, where I and j different from each other. Because if it were, then I could just throw out Gj. Okay. And the other thing I'm going to demand is a simple thing, which is I can make these guys monic. In other words, if the leading term is 2x squared, then I can just divide that polynomial by 2, and that'll just make my numbers a little nicer. So each initial term is monic. In my example over here, of course, the initial terms are already monic. They're x squared and y to the fifth. But if I had an initial term of 3x squared, I could just divide the whole polynomial, this whole polynomial, by 3, and that would still be a minimal Groebner basis. That will still be a Groebner basis, and it will be a better one according to what we think. Okay. So that's minimal Groebner basis. And there's a very nice fact about these things, which you will prove in homework 2. So one of the homework questions in the next homework is going to say that any two minimal Groebner bases have the same number of terms and the same initial monomials. any two minimal Groebner bases have the same number of terms, same number of elements, and exactly the same leading monomials. So that's a nice property. That means that that ideal really is the minimal Groebner bases all are going to have two terms, and those two terms are going to be x squared plus something and y to the fifth plus something. And the only thing that can change is the plus something. Okay? So that's one thing. Okay? But once you know that, that tells you that there is some kind of uniqueness property here. That two minimal Groebner bases are they sound like they're kind of the same thing. And maybe you can ask for a very good Groebner basis, and that's what we're going to do. We're going to say that a minimum Groebner basis is reduced if it is minimal and more things. So we're going to demand the same first property. You have to be monic, but here we're going to demand something a little bit stronger, which is that not only is the initial term not a multiple of, not only is the initial term of Gj not a multiple of any other initial term, I'm going to demand that no term in Gj is a multiple of any initial terms. So no monomial in Gj is a multiple of the initial term of a different generator. Okay. So I want you to look at that minimal Groebner basis and tell me if it's reduced. In the meantime, I'm going to say something easy, which is that reduced implies minimal. So this is the first thing. Second thing is that reduced implies minimal, because of course this condition is stronger than this condition. So is that reduced? It's not, right? So to see whether this is reduced, we have to check, are any of the terms of this guy multiples of this leading term? Well, no. Y to the fifth is not a multiple of x squared. Y squared is not a multiple of x squared. And we have to check, are any of these guys multiples of the leading term of this guy? And that is a problem, right? Because this term is a multiple of this guy. Okay? So this is not reduced. And then the natural question is, okay, well, how do I reduce it? And the point is that, like we said, the key thing that makes this a Groebner basis is having x squared here and y to the fifth here. So how can I change this polynomial while keeping the x squared but getting rid of this guy? Well, it's kind of clear what I should do, right? I should just subtract x times this guy, and then I'll be able to cancel this xy to the fifth and see if that's reduced. And kind of keep doing that. Okay? So that's basically what you can do. So maybe let's do it in this specific example. So since this guy is not reduced, what I would do is that I would take x squared plus xy to the fifth plus y to the fourth and reduce it modulo the other guy. Okay. And basically what you're going to find is that modulo this guy, y to the fifth is equal to y squared. And so when you perform this division, just this y to the fifth is going to become a y squared. Okay? And so that means that I can form a different Groebner basis that looks like this. Okay. And now this is reduced because none of these monomials are multiples of x squared. None of these monomials are multiples of x to the fifth. And so this is a reduced Groebner basis. And reduced you should think of as very nice. I'll show you just how nice in a second. Okay. So by the way, you might think about this as being something very similar to something that you are familiar with in linear algebra. Let's say that you have a vector space and you want to find a basis for it. Then you can first just kind of pick a random basis and you're happy. But then you might get pickier and say, well, maybe I want a nicer basis, like an upper triangular basis or one of these things. And if you think about it, this is basically what I'm doing here. So it's philosophically, it's very similar. Here I have a basis, but I don't like it. And so what I do is that I kind of use combinations of the other polynomials to reduce this polynomial into something that I like. If you think about this, this is exactly Gauss-Jordan. I mean, philosophically, you kind of take, if you have a basis for a vector space, I don't know, let's say for example you want to make it orthonormal. If it's a Euclidean vector space, then what you do is it doesn't start out orthonormal, and you make it orthonormal by changing each vector using multiples of the other ones. So you had an ugly basis, you make it into a nice basis. And this is the same philosophy. You have a Groebner basis, and you make it into a reduced Groebner basis. Now here's a theorem. Which is that given an order, a monomial order, and an ideal, then there is a reduced Groebner basis. Okay. But the nicest thing about it is what I haven't written, which is that this thing is unique. So if you think about it, this is pretty amazing because it means that, I mean, I could have started with very different generators for this ideal. And I could have obtained a very different list here. I could have obtained a very different Groebner basis here. Even when I made it minimal, I could have made it very different. But when you reduce it, it's always going to be exactly the same. You're going to get this polynomial and this polynomial. That's a good question. So the question is reduced the best possible Groebner basis or not? And the answer is that it depends. I would say that very often reduced is the nicest possible thing, but sometimes you want different things. For example, I'll give you an example. There's something called a universal Groebner basis, and that is not as nice. It doesn't have this nice property, but it has the property that you can change the monomial order, and it'll stay a Groebner basis. And so that's a useful property. So it just depends what you're trying to do, but for a lot of purposes, reduced is the nicest that you can hope for. Okay. So how do I prove this? One of the nice things is that the proofs are so easy. And you've seen that every single proof that I've done fits in a board, and this one also. So proof. Well, we know that Groebner bases exist, so let's start with one. So let G start. I mean, this is a proof slash algorithm, by the way. I'm going to tell you how to do it. You start with a Groebner basis, no matter which one. Then you make the first thing. You make it monic. So you make each initial. So let's call this guy G1 up to Gn. So you make each initial term monic by just dividing. Okay. We're going to do basically what we did there. So we make it monic, then you throw out things that you don't need. So you remove any unnecessary GJs, and those are the ones such that the initial term of GI generates the initial term of GJ for some I. If this is the case, then you don't need GJ. Then you're going to do this reduction process. So you're going to say, okay, well, if each GI has no terms that are multiples of the initial terms, then I'm okay. But if it does, then I'm going to divide. So for each I, I'm going to do this. For each I, I'm going to divide GI by the other guys. And this notation, as you may know, means that I take the whole set, except that I take out GI. I do this, and then I let Ri be the remainder. Okay. Now, if you think about it, what do I want to say here? I want to say that basically I didn't touch the initial terms, right? And so that means that Ri and Gi have the same initial term. Why is that? Because Gi had this initial term, and I couldn't have canceled it by dividing by the other G's because none of the other G's have anything that is a divisor of this guy. So this guy could never be canceled, and it's still going to be the leading term of Ri. Okay? And then what you can see is that these Ri's are your reduced Groebner bases. We're actually out of time, and I don't want to keep you guys, so maybe we'll stop right here. Think about this and make sure you understand it, and I'll talk about uniqueness next time, which will take me maybe half of this board. midnight.
I'll do that before.
On email by midnight.